Good morning, grade 12s, and yeah, so we're gonna start our well, pretty much our last unit here, and I really love these last couple of units in the course, and I think you'll find it well. There's some things that are a little weird, a little confusing, but I think you'll find the math and the problems pretty straightforward. So. Anyway, we'll take a look at it, and it's completely different from the stuff we've been doing. So there's no free body diagrams or anything like that. So it's kind of a break, and it's more getting into modern physics, which is nice too. And yeah, so I have a new unit outline posted. Okay, I'm just going to say a couple of things about this. You don't really have to do, just to save you some work. Okay, let's get rid of this. You don't really have to do that, okay? And also, what I'm going to do today is I'm going to make this lesson number 1, okay? So I'm going to start with sort of the history, so I'm going to put that up here, and you can cross out this lesson number 1 here. Okay, so lesson number 1 is really lesson number 6. So your assignment is going to be this little thing that I've just highlighted right there. Okay, so in a table, compare these things. This table is in your textbook, so you'll find it in the text, and it's a little, like, here's your little challenge, is to find that table and like just read it and sort of summarize it in your notes. I'm going to go through some of it here today. Okay, and then that's not it for the week though. Like I'm going to get, I think for this week, we're actually going to go through a couple of other of these things, like probably lesson number 3, and also, yeah, lesson number 4, some of lesson 3 and lesson 4 for this week, okay? And then, you know, we'll get through the rest of the unit next week. And then we have just one thing left after that, the quantum, and quantum is actually really fun. So, all right, so let's get to it. So this whole thing, what is light? And light, this has been a really sort of cool question for a long time in physics. Okay, so the question of what is light, okay, like physically what is it, has been around for centuries, okay? And it turns out that the answer to that question has led us to places that are extremely strange and bizarre. Okay, like what I mean by that is it has turned science sort of upside down, and you'll see when we do that in the you'll see what I mean when we do quantum physics, where things are really strange. Okay, they're actually weird. Okay, it's actually a thing in science called quantum weirdness, and it all started with us trying to understand what light is. So it's a really great story. Okay, and so in this unit here, it's called the wave theory and light, the unit. So you'll see what we thought light was, okay, about 100 years ago, okay, but we're going to go back a little bit before that in time, okay, but before we can really talk about any of that, we need to understand the basic properties of light, okay. So properties of light. 1, I'll switch to black here, okay. The first one is called rectilinear propagation. And that is just a fancy way of saying that light travels in straight lines. Okay, so if you go back a few hundred years, like the time of Isaac Newton, and like Isaac Newton, famous scientist, right? He's like the Albert Einstein of his time, okay? So he's considered one of the world's greatest geniuses, and people asked him, what do you think about light? What is light? Because we don't have a good theory for light. So you're a genius, why don't you come up with something? So he did, okay? And any good theory, you would have to explain the known behavior for light. So here you see these rays of light here in this picture, they all look perfectly straight, okay? So light rays are straight. Think of a laser beam, how straight a laser beam would appear, okay? So that's the deal, okay? Light rays seem perfectly straight. Now, if you throw a ball, balls do not travel in straight lines. They travel in curved paths because of gravity. Okay, so Newton hypothesized that light, like a ball, also follows a curved path. So it only appears straight because the velocity of the ball is, or the light, sorry, is so high. Like if you could throw, let's say you shoot a bullet out of a gun, well, the path of the bullet will seem straighter than the path of a tennis ball that you throw. Okay, and the reason why is because the velocity, the muzzle velocity of the tennis ball of the bullet is so high. Okay, and so that's the deal with Newton. Is Newton thinks that light actually does bend because of gravity, doesn't follow a straight line, but because the speed of light is so incredibly high, it only appears that it's traveling in a straight line. Okay, but it's not perfectly straight, so it would have a slight curvature to it. And actually, okay, what we'll learn about in sort of the future, when we move into the future, Newton was kind of right about that. Okay, light is affected by gravity, but there was no way for him to measure that effect in his time. Okay, it took hundreds of years later where they were able to measure that. Okay, but light rays appear straight, so a good theory needs to explain why they appear straight. So that's it for rectilinear propagation. Light seems to be traveling in straight lines. Okay, all right, number 2. For number 2, I have this phenomenon. Okay, so number 2 is diffraction. Okay, so what is diffraction? Well, diffraction is light spreads out after passing through, okay, a narrow opening, like a pinhole or something. Now this phenomenon is called diffraction. Okay, and here you can see it visualized here. So if you have like a fairly, here's the source of light, it looks like a sort of a plus sign, okay, and it's shining through this large hole that you see over here, you get an image over here on the other side, okay. Now if you make the hole smaller, the image will appear slightly sharper, but there's always a, I'll use a rainbow color, there's always a fuzzy edge. Okay, now if light goes through a tiny hole, here we can see the fuzziness has a weird sort of ring sort of pattern to it. So here, the fuzzy image is due to the spreading out of the beam. The beam spreads out, okay? And here you can see the beam spreading out there. So light's still traveling in straight lines, it just seems like one line is becoming many lines, right, as it passes through the hole. And the smaller the hole, the more pronounced the effect. So here, with a smaller hole, the effect is more pronounced. Okay, so that's diffraction. Now, I mean, I can draw a picture for it. Like usually I show students like this. Let's say this is a barrier of some kind, like a piece of paper with a small hole cut out in it. So here's the hole, and let's say you have a beam of light. I'll make it blue. This beam of light comes through here like this, and what happens here on the other side is it spreads out. Okay, and this is called diffraction, this phenomenon. So that's diffraction. So what I'm trying to do is summarize for you what the known properties of light are. Okay, so if, like for example, you know, we know that light travels in straight lines. We know that light spreads out when you pass it through a pinhole, let's say. And so if you're going to come up with a theory, let's say you're a scientist and say, all right, I need you to come up, what is light and why does it do these things? Well, it has to explain, your theory must explain these behaviors, right? All right, next one's really easy, reflection. Okay, so here you can see someone with a laser doing the experiment. Here we can see that light travels in straight lines very nicely with the laser, right? Those lines appear perfectly straight. Here it's shining off of, this is a mirror. Okay, and I can summarize reflection just by saying one thing. that the angle of incidence equals the angle of reflection, okay? And if I zoom in on this picture here, this is the angle of incidence with the laser coming in, and this is the angle of reflection, okay? Measured from there, angle of reflection. And this line here is called the normal line, and we talked about that in grade 10 optics, okay? So if you like, I can draw another picture of it for you here. Like here's your mirror, okay? And here's your laser beam coming in. It hits this, bounces off like that. And then the normal line, just like the normal force, perpendicular to the surface of the mirror. Now it's just an imaginary line. So this would be your angle of incidence. This is your angle of reflection. And those two things are equal. And that's what light does. In fact, if you throw a tennis ball at the wall and it's not spinning, it'll obey that law too. Okay, angle of incidence equals angle of reflection. It's called the law of reflection. All right, so next, refraction. I guess this was number 3. Okay, number 4 is refraction. Refraction is what happens when light bends as it's entering or exiting something like glass or water or something like that. Okay, so here you see a picture of air and glass. Okay, and what happens is light will bounce off the glass. That's just reflection, okay, off the top. But light also goes through the glass, and so when it does that, though, it changes direction, and there's a bending in, like, you know, like the light was supposed to go along this straight line here, but it didn't do that. It bent, so that incident ray of light got bent, and that's refraction. So refraction is the bending of a light ray when it enters or exits a medium and enters a new medium, right? So a medium is like air, you know, or glass or plastic or diamond or whatever the case may be. Okay, so that's refraction. All right, there's one more, number 5. Number 5 is dispersion. And dispersion I can summarize in one word: rainbows. Okay, so rainbows are a known phenomenon. Okay, and Newton was able to manufacture glass blocks, like this glass prism that you're seeing here is a triangular shaped glass block. When you shine light through the triangular shaped glass block, what happens is the white light will spread out and form the colors of the spectrum. Now, I will remind you that they've taken indigo off the list. Okay, indigo is supposed to be the color of blue jeans, actually, so you don't really see it there. But anyway, yeah, they've taken indigo off the list recently, so it's just Roy G. Biv, okay, instead of Roy G. Biv. All right, so yeah, so what happens is white light seems to be comprised of these other colors. It separates out into these colors, and this is what ultimately creates rainbows. When raindrops behave like little prisms, and then the white light coming from the sun creates a rainbow, you know, when the sunlight is shining at just the right angle on the water droplets that are suspended in the air while it's raining. Okay, so I'm just going to say white light separates into the colors of the spectrum. When exiting glass, for example, This is just for example. Could be water, could be glass, could be diamond. In fact, diamond does it way more often than most other medium. For example, near what's called the critical angle. And we'll talk about that more when we talk about refraction in more detail. All right, so there you have it. We have 5 known properties of light. There are more, okay, that we're going to get into later, but there's 5 known, these 5, okay. So like if you're talking about at the time of Isaac Newton, so about 300 years ago, okay, we had rectilinear propagation, so he knew light travels in straight lines. We had diffraction, okay, we had reflection, and we had refraction and dispersion. Now, you know, scientists at the time would have known that light travels very fast. Attempts were made to measure the speed of light, and they were all not successful. It's just too fast, especially for the technology at the time. We were only able to measure the speed of light about 100 years ago or so. Okay, so maybe in the late 1800s. So Newton was 200 years, you know, out of time there, right, for him to be able to measure the speed of light. Okay, so anyway, these are the properties that they knew about 300 years ago. So now I just want to talk about your first assignment. Okay, like I said, we're skipping to lesson 6, a little history here. So in a table, compare Newton's model, okay, to Huygens' model, okay, and you want to explain those things: rectilinear propagation, diffraction, reflection, refraction, okay, and dispersion. So how do these two guys, like here's the deal with them, and I'm just gonna maybe go back to the notes for a second. The cool thing about it, okay, and I love this story. You probably never heard of Christian Huygens, but Newton you've heard of course. Okay, so look, Newton had what's called a particle theory of light. And he called the particles corpuscles. We call red blood cells corpuscles, by the way. Okay, so here's Newton's theory in a nutshell. He thought light was a beam of particles. So like, let's say I hit you with a flashlight, okay, light, not the flashlight itself, okay, just the light from a flashlight, shine it on you. Do you feel anything? You know what I mean? Like, are you being hit by a beam of particles? Sort of like wind, right? Like if you're standing in the wind, your wind is actually a stream of particles, right? Air molecules. And when it hits you, you feel it. Okay, but what about light? Well, you don't really feel it, right? Now, you do feel heat sometimes, say from the light of a fire, but you don't feel like it doesn't blow your hair back, right? So the thing is for Newton is he has to show, like, you know, if light is really a beam of particles, how come we don't see some of the other characteristics of particles that we would normally see, okay? So, like for example, did these particles have mass? Now, according to Newton, these particles do, light particles do have mass. Okay, and in fact, one of the things that he proposed was that if you were a red particle of light, you would have more mass than a blue particle of light. Okay, so he thought that colors represented particles of different mass. Okay. He theorized that these particles were incredibly small. Way smaller than, for example, the particles that make up matter. Okay. And that's why they were able to pass through things like glass. Okay. Whereas, for example, if you throw a ball at glass, it will never make it through because it's just too large to fit between the spaces between the molecules of glass. Okay. So anyway, Newton had this particle theory, and he used it to explain the 5 things that you see above. Now, I want you to actually read those explanations and summarize it in the table. Okay, and there is a table up like this in your book. A simple assignment. You just have to look at that table. Don't look anywhere else. Don't go online. Okay, and look for it. You'll find it's too complicated. Okay. Now, anyway, at the same time, there's this guy named Christian Huygens, and he is a contemporary of Isaac Newton. Okay, and he came up with a wave theory of light. Okay, and he had a problem. See, I'm just going to say one of the things that Newton could explain. Newton's theory explains very well how light can travel through space, which was another known property of light, right? That it makes it from the sun to the earth. And space, there's no medium, there's no particles, right? Like this, it's just empty space. So waves, the thing about waves is that they do require a medium. Something has to be waving. Water waves require water. Sound waves require air. There's no sound in outer space because there's no medium to carry the sound in outer space. So anyway, Huygens had this problem, but he still proposed a wave theory. So light is a wave, okay? And he proposed a mysterious medium called ether. You might have heard of it referred to on, like, in the Avengers, for example, the Dark World, where they talk about, like, in the beginning there was this weird ether, one of the Infinity Stones, you know, something like that. But anyway, ether is considered this medium that is everywhere in the universe that light is able to travel through, and that's how light is able to make it from the sun to the earth, through this ether medium, according to Huygens. Okay, this was a real weakness in his theory because no one could measure the ether, okay, at the time, and no one's ever been able to measure the ether to this very day. The simple reason is it doesn't exist. Okay, but anyway, that doesn't mean Huygens is totally wrong. We'll get to that later. Okay, different colors. Okay, for Huygens, it means different wavelengths. Okay, so that's very different from Newton's explanation, right? Okay, yeah, anyway, that's basically it. So Huygens has this wave theory, okay, and one of the things about a wave theory is waves have a property that's not listed in the 5 properties above called interference. And I'm going to put a question mark beside it. If light is a wave, then we should see interference of those waves when 2 light beams intersect, let's say. But actually, Huygens was unable to observe interference at the time. Okay, so there was a few questions about Huygens' theory. It turns out that for about 200 years, Newton's theory was preferred and taught in school. And then 200 years later, everything changed. And everything changed in the mid-1800s when this guy named Thomas Young did a famous experiment that basically proved that Huygens was right. Okay, so anyway, I spelled different one here. Let me fix it. So we'll get to that later, but of course this unit is called the wave theory of light. So spoiler alert, okay, Huygens was onto something here. Okay, so but anyway, the story is really a great story, so you'll see how it plays out. But what we're going to do is we're just going to look at these things, and then in the next lesson that I'll give later this week, we'll show how evidence came to light in the, pardon the pun, came to light in the 1800s that basically proved that Newton was wrong and Huygens was right. And they figured out how you could get through a vacuum without any ether, and that was very important too. So they had to modify Huygens' theory a little bit. There was no ether and stuff like that. But like you know, he was definitely more correct than Newton was. Okay. All right, so that's it for today. You have your assignment. Your assignment is just basically to write out some notes here, and then I'm going to show you a little video of comparing these two theories later on, okay, and show what evidence came to light, okay, in the next video. All right, so guys, enjoy that for today, and I think you'll find this assignment pretty easy for now. All right, so we'll talk to you soon.